So let's begin the afternoon session. And first up, we have a panel discussion chaired by Yang Wei from the London Institute of Mathematical Sciences. We have an exciting panel which he's going to introduce, and they're going to be talking about ML applications to problem solving, universal and specific features. Thanks.
Thank you very much. It's a great honor to chair this session, and thanks to Suresh and my co-organizers for this very exciting 3-month workshop. I hope that you are enjoying. So I have the pleasure to present first, introduce the panelists. Let me just go in alphabetical order. And the first happens to be my dear friend, David Berman, whom I have known for many, many years. He did his PhD in theoretical physics and mathematical physics from Durham in string theory, and has held academic positions in Cambridge, and now is a professor at Queen Mary University of London, and jointly working as the head of AI for Cambridge Consultants. He's one of the very few academics that I know who has joint positions as a professor in a university and gaining extra cash on the side. And the other panelist is Professor Andrea Liu, I think, who was just in the process of. Oh, this is great. This is the grand entrance, so I can continue to sing your praises, Andrea. So Andrea Liu had obtained her PhD in theoretical physics from Cornell, and has held academic positions in UC Santa Barbara and UCLA, and is currently the Hepburn Professor of Physics at UPenn. And in fact, I also know Andrea, if you remember me from my postdoc days with Bert Overood at Penn. And so it's an honor to be chairing this session with you. And Andrea specializes in condensed matter theory. And very interestingly, she's currently the Kirk Distinguished Visiting Fellow for this for the soft condensed matter program, and we're very delighted to have her. She's visiting Cambridge anyway, and we're very delighted to have her present at this Black Holes meeting. And so this is very much, as you can see, the panelists have very diverse backgrounds. Moving on, Thomas Fischbacher, who is online, you can see, and had his PhD in theoretical physics from the Max Planck in Potsdam in string theory and supergravity as well. So I don't know Thomas personally, but I've certainly have read his papers. And so he has had academic positions in Brussels and Southampton before moving on to Google research. So this is our industry expert. And finally, and certainly not lastly, just because we're going in alphabetic order, we have José Miguel Hernández-Lobato, who is local to the University of Cambridge, and he obtained his PhD in computer science in Autónoma in Madrid, and has held academic positions in Cambridge and Harvard, and is currently a professor of machine learning in the engineering department at Cambridge. So it's a pleasure to welcome our panelists. So I'm going to make this as open-ended as possible, partly to reflect that I'm never prepared for anything. So I'll leave to the preparedness to the experts. This is a panel on the context of machine learning in the sort of as emergence of knowledge, and in its universality in solving problems, which is something I'm deeply concerned with. I mean, I also started myself as a mathematical physicist. But I have very wide interests in how AI is going to help us solve problems across the disciplines. And my colleague Misha will chair the next panel on the ethical and societal impacts of how AI is affecting us. And this is actually very timely that we're having this, because as you well know, that last week was the Rishi Sunak's summit on AI safety and AI governance. I happen to be very honored to be in the pre-summit at Ditchley Park, at Ditchley Manor, to the Bletchley event, and we were talking about AI, the existential threat of AI. But that's not what this panel is about. This panel is a much more optimistic panel about how AI is going to help us solve problems. So maybe to kick off, maybe we'll start with Andrea, since we're going in this essence. So given your background in physics, how do you see machine learning contributing to a new ontology of knowledge building? And what aspects of traditional physics thinking can be extended or challenged by machine learning? Please, Andrea.
Yeah, so we used it in automatically on. Yes. Okay. We've used it in a couple different ways. The first one was for work on the glass transition, which is, you know, one of the oldest unsolved problems in condensed matter physics, at least according to Phil Anderson, and sadly, it's still true. And for years, so the structure as you cool down a liquid hardly changes at all, but the dynamics, the relaxation time to equilibrate the system can grow by like 10 orders of magnitude in tens of degrees. So it's a really strong increase with no structural signature. And so people have been looking for structural signatures of glassy dynamics for a long time. And we discovered that with very simple machine learning methods, basically any kind of method you choose, it pops up very easily. You can find a structural order parameter for glassy dynamics. So, and then we could build theories based on that order parameter and stuff like that. So that was one thing. But I think a more profound thing is that the way computer scientists solve inverse problems, because the whole thing about training a deep neural network is to solve an inverse problem. What network gives you the desired output? Is really useful in physics because we want to design systems that have given properties, and to do that by introducing learning degrees of freedom that are like the node weights, and then just minimizing some cost function to get that, turns out to be a wonderful way to design materials to do special things, to have properties that they would not normally have. And the only difficulty is because they are physical systems, you must simultaneously satisfy physical constraints. For example, if you're a non-zero temperature, you have to minimize the free energy. So you also have physical degrees of freedom, as well as learning degrees of freedom, a physical landscape, which is the free energy landscape, as well as a learning landscape. And you have to minimize in both landscapes simultaneously. So it's got that caveat, but it's a very powerful way to design new materials. But it feeds back because when we realize that you can do so much on the computer, but global gradient descent is really costly. And so, which is the same problem for deep neural networks. And so we started thinking about how to do it scalably, and we came up with local rules that approximate gradient descent. And then using that, we were able to develop actually simple electrical circuits that learn by local rules. So you don't need backpropagation, you don't do any of that, and that can perform then machine learning tasks on their own without a computer. So sort of, I think the connection goes both ways.
Interesting. So since we're on topic of physics, and I see Dave nodding his head, and would you like to comment on how this kind of paradigm has respected your area of research?
So those of you who were in my talk this morning, that was about the use in biology actually, but it's like the spin glass problem in the following way. In physics, you know, when I was brought up as an undergraduate, you could solve essentially 3 problems, maybe 1 body, 2 body, and an infinite number of bodies. And then anything more or in between that, you were stuck. And then you went to a computer and then maybe you could do a few thousand, whatever, depending on how computers worked. Somehow with machine learning, we have a different paradigm where we take huge amounts of data with a view that we can now model much more complex systems and find simple descriptions of them in some sense. Finding that balance of how much data you need and what constitutes a useful thing is actually the work of what we've got to do. We can't just take an off-the-shelf model, run it through blindly and hope for the best. But there is a different approach where obtaining a model and understanding what the model does provides us with insights. And we've seen that across the board in systems like biology and other areas. I'd like to respond to the final bit, which really interests me, and I will chase you up afterwards. I am really fascinated with it going the other way, which is what physics can do for machine learning and AI. So the work that I've been involved with is applying renormalization group ideas into learning. It's clear a lot of the intuitions in quantum field theory, because they go over into statistical interpretations, are relevant for learning problems. And I'm sort of fascinated by not just, and I sound like Kennedy, not just what ML can do for physics, but what physics can do for ML. And I think it's really a two-way street.
That's a very interesting thing. I think this is an emergent, a continuing theme which is more recent. There's been a lot of work on mathematics for AI, and recently, but then there's also this feedback of AI for mathematical discovery and fundamental science discovery. And just to turn this a little bit to José and to Thomas, I mean, do you feel there is, in machine learning research, there's a shift towards more data-driven, as Dave was mentioning, and less rule-driven or rule-based paradigm for both of you?
Yeah, maybe I can say a few words on this. So I was lucky enough to start working in machine learning a very long time ago. In 2005, I was starting my PhD in machine learning, and I was experiencing all this shift in machine learning during the last 2 decades. And we have seen like a very big revolution in the field. At the beginning, there was a lot of focus on methods that were efficient, learning for less amounts of data. For example, you had like support vector machines, Gaussian processes, Bayesian non-parametrics. These were methods where people focused a lot on introducing prior knowledge into the models. And then you were able to perform quite well in this low data regime. But now, with the advent of deep learning, we have now methods that are more scalable. They can run on larger amounts of data. And you can see that in that regime, then the larger amounts of data always wins. So you could have like a model that introduces maybe a lot of fancy prior knowledge, but if the method is not scalable, another method that is scalable and uses less prior knowledge will be able to perform better. And we have seen this success. It's quite interesting because the field has changed quite a lot, but I think there is still quite a lot of work to do, especially in particular domains. We have seen that deep learning is very successful, but even introducing additional prior knowledge, like for example, symmetries or invariances in your models, they can still make like huge gains. And you have a bit the advantage of both things. You have a method that incorporates useful prior knowledge, and you have methods that are scalable and they can learn from large amounts of data. I think right now there is like a very exciting time for deep learning, where you have a lot of people working in this area, trying to combine deep learning methods with better models that capture the invariances or irregularities or patterns present in the data better.
Thank you. And Thomas,
Yes, thank you. So I wanted to expand a little bit on David's point that this is a two-way street. So if we look at the deep learning revolution, which you could say Jeff Hinton kicked off with his 2006 paper, then depending on how you read this paper, you might actually sense that there's quite a bit of intuition, in particular on Jeff Hinton's side here, behind his thinking that you can tie to statistical mechanics, thermodynamics. So I see quite a bit of Gibbsian thinking in his approach, and this certainly has helped a lot to enable him to see that, yes, you can make deep learning work, you can train deep architecture so that you really get a benefit from that extra depth. And you find it in many places in machine learning. So for example, there was this 2016 paper by colleagues of mine, deep information propagation, which took a statistical mechanics perspective on this problem that everybody knows from introductory lectures about vanishing gradients. So the thing is that if you approach this question, why do we observe vanishing gradients, in terms of phrasing it as a percolation problem, then you can use fairly basic mean field theory to study this, and you can actually show that it's basically a problem of two parameters, and you can choose them such that out of the box you can train quite deep architectures with just a little tweak. So there's a lot of deeper understanding of what's going on that's coming in particular from statistical mechanics and thermodynamics. And personally, I mean, we of course get a lot of candidates here at Google Research with all sorts of backgrounds, but most of them machine learning. Personally, I would much appreciate if more of the people I'm working with had a somewhat deeper background on thermodynamics thinking, because overall that's very useful.
Thank you. Oh, by the way, please raise your hand. I mean, I know there's a formal Q&A session, but if you have any questions, raise your hand in the middle to ask any of these experts. I mean, this is a great opportunity to ask questions any time. So just raise your hands. Any questions at this point? So far? Yes. Yeah, or follow up. Yeah, of course. Make it interactive. This is what's going to make us human and not AI.
So in comparing, I'm basically a condensed matter physicist, right? Many body systems. And when you think about learning as an emergent phenomenon in a many body system, right? I think artificial neural networks and also the brain are fundamentally different from the normal kinds of matter that we usually think about. In condensed matter, sort of the motto, I can't believe I'm quoting Phil Anderson again, but he said more is different, right? And he means more is different from one. The behavior of many is different from one. But many more is not very different from more. And that's why computer simulations have been useful. You can study a system of 1,000 particles and really understand what's happening in, 10 to the 20 a real experimental system. You can get a pretty good idea. And that's not true for artificial neural networks, for deep neural networks. The bigger they get, really, the more complex things get in a big hurry. So the many more is really different from more. That's why they've been so different. Or you think of brains. C. elegans has 302 neurons. We have about 10 to the 11th. And you think about that difference, it's not a simple, oh, the phase transition got sharper or something like that. It's really a huge change of cognitive abilities. And I think that's a fascinating problem for a many body physicist to say, okay, when is many more different from more? And it really comes from having all these learning degrees of freedom that increase as their system size increases, that you can then tune to get properties, which we don't usually have in physics. And so I think that's another way that, machine learning ideas really pose interesting physics problems.
Mm. That's a really good, the difference between more and many, right? That's any other comments from the panelists on this point? I find that very fascinating. I'd love to hear what you think about that.
I mean, this is sort of a technical thing, but there's been this work by Greg Yang, which deals with exactly how things scale in hyperparameters as you scale networks. So before that, there was this thing that actually neural networks have a similar property of physics, in that when you take the number of neurons to infinity, you can actually solve that problem, which is a weird thing when you first hear it. But indeed, there is a large n limit and you expand around, in fact, a Gaussian theory. And they're modeled by a GRP, which is extraordinary. Then you can do perturbation theory around that the other way, which some people have then done. And then people like Greg Yang describe how you can take multiple scaling limits in parameters and preserve the properties of the model. But his path is exactly trying to find the balancing act that you're saying doesn't happen. So you're right, it doesn't happen generically, but his work, which was very useful, says that you can find a way of scaling in a very fine-tuned way so that as you scale and go up in degrees of freedom, you exactly mimicked the properties down below. That was immensely useful for companies who wanted to do tuning of those neural networks, because it's incredibly expensive to do a very large neural network. And if you can make it scale in that very fine-tuned way and match what goes on down below, you do really well. But that's a very fine-tuned way. But just, it's interesting that it exists, that in this, because we talk about scaling, but it's a multi-dimensional way of scaling, because you're each layer and all sorts. But yeah, it's the scaling of degrees of freedom is a very non-trivial one.
Yeah, of course, absolutely.
Yeah, talking about scaling neural networks, I was thinking about the thesis of Radford Neal, which was basically the first person that looked at what happens if you take a neural network and now you make the number of hidden units in this network go to infinity. And he actually showed that in the end, the model converges to a Gaussian process, and then you have advantages like exact inference and so on. But something that he also mentioned in his thesis, which is extremely interesting, is that as you increase the number of units to infinity, each unit individually contributes less to the output of the network. And in the end, this means that the neurons, they are no longer really learning specific features that are useful for making predictions. So you could imagine that you have a neural network that does maybe image classification, and you have maybe neurons that learn to identify faces or objects. And then these neurons, they're identifying patterns. When you make the number of units go to infinity, this property is lost. And then you end up with something like these Gaussian process models where you don't have any really learning of specific features. You just have a fully non-parametric method where all the data points are useful for prediction, but you lose this property. So going back to the thesis of Radford Neal, he said this is actually a property of the Gaussian. You have usually a Gaussian prior on the weights of your network, and as you increase the number of units in your network to infinity, the magnitude of your weights should go towards zero, because otherwise the whole network will diverge in its output. And then what happens is that if you have a Gaussian prior on these weights, then all the weights will be super small. And something that is quite interesting in his thesis, he mentioned, oh, maybe we can use, instead of a Gaussian prior, some other prior that has heavy tails and will allow for weights that have eventually very massive magnitude compared to others. So you could imagine that you have an infinite number of units, all of them have very small weights, most of them have very small weights, but once in a while, you will have units that have massive weights, and they will make like a very significant contribution to the prediction. And in this case, you would have like the advantages of both. I mean, you would still keep the advantage of learning individual patterns. That sounds great, but doing inference in these models, when you move away from the Gaussian prior, is extremely challenging, and no one has ever managed to do anything. He mentions, for example, to use alpha stable distributions, that are distributions that are known to have heavy tails, and then you will have weights that are very concentrated around zero, and then some other weights could be massive and very large. That's like a very interesting idea, but no one has been able to work with these models.
There was a question, yes.
You have a previous meeting a few years ago now. There was a discussion about brittleness inside machine learning, and it sort of the implication was you can have one, you can have many, you can have much more, but you can have too much. And actually, it allows solutions which are non-integrable and become ineffective. And I don't know if there's been any progress on finding that upper bound where there's just too much too many parameters to actually provide a credible solution.
Yeah, I think this is one of the big limitations of machine learning methods. I think they can be extremely successful in very specific settings, but as long as you move them away from maybe the training regime or the data that the method saw at training time, they can behave in unexpected ways. And this is a very open problem in machine learning. You can see, for example, examples with these Tesla self-driving cars. No, there are videos in YouTube where you have a Tesla car in front of a wagon pulled by horses, and the Tesla car says, "Oh, this is a truck driving towards you." And the neural network inside of the car never saw a wagon pulled by horses before, and then the predictions that it's making are completely arbitrary. And that's an important problem. These methods, they can be extremely unreliable in these settings, and it's a problem that many people in the machine learning community are working on. I'm actually working in this area. I work on trying to capture better uncertainty in the predictions of machine learning methods. And the idea would be that when you see a data point that you have never seen before, you would like your network to have high predictive uncertainty, saying, okay, I have no idea what should my prediction in this case. And then, yeah, as a user, you would then at least be able to handle this situation or to inform the user, or maybe you need to collect more data in these settings. You could give an alert or something. And right now, many methods, they don't really do anything. They just fail catastrophically in these settings.
So
just very quickly, respond to that very
well,
quickly.
yeah.
One of the techniques which I absolutely love is Bayesian methods, because you'll get back a probability distribution rather than just a prediction. And somehow I'd love to capture some of that when we're doing modern ML. So you're not just giving an answer, but a confidence, which I think, but you know, Bayes had it. It's just we couldn't do Bayes with enough degrees of freedom. So, but the idea was great.
Just had to put aside Bayes. It's like a religious.
He's buried in London. Question from Professor
I'd
Miguel.
like to discuss the following issue. In my scientific career, I applied machine learning to some physics problems like distribution of vorticity and the turbulent flow, where the things are repeatable. It's random, very complex, multi-dimensional function you have to learn, but it is repeatable. The more data you have, the better you could, in principle, reconstruct your function if you properly guess the features and the learning algorithm. However, in my other scientific life, rather recently in a big organization, there were several bright scientists, experts, then maybe 20, very bright people representing machine learning, and we tried to apply machine learning to finance, to predict the stock market. And here we encounter the problem that there are two kinds of phenomena. The ones which are repeatable, which are basically related to human nature, to reaction of the investors and society to fixed perturbation. It's like we have a big pond and giants going around the pond and dropping huge stones, and we more or less can compute the shape of the circles. There is some repeatable patterns, but on top of that, there is an unknown thing which is related to when this giant would drop that boulder in that pond. So there are some unpredictable, non-repeatable events. And on top of that, there are repeatable. And the challenge for the machine learning is to be able to combine. And the solution was to combine human intuition and some heuristics with machine learning. Basically, once the big stone is dropped into the pond, then we start predicting. We don't want to really predict at larger intervals because we don't know these unpredictable events. So is there a systematic way to learn non-repeatable, non-stationary probability distribution with two kinds of time scales? bigger time scale and a smaller time scale. How to combine that? It's called something like name. It's not learning. It's really some evolution with feedback. So you learn some patterns, but you also take into the process some unpredictable things. So is there a technology, technique, or science, some modification of learning techniques which would take into account that real phenomenon?
Yeah, so the problem you mentioned is really complicated, and it depends on the particular problems that you may be interested in solving. I can give you an example of a particular problem that maybe has these properties, and I can tell you a bit how some researchers came out with some possible solutions. This is work done by some members of the machine learning group here in Cambridge. Some particular problem where machine learning methods have been very successful is in the in accelerating solutions to differential equations. Now you may have like a particular initial condition, and you may have some differential equations that explain how your system evolved, and then solving the differential equations numerically could be very slow. But you can actually pre-train based on data some predictor that will output the next state ahead, where you speed up the process. You don't have to solve your differential equation, and then you can just accelerate the whole thing. So that sounds great, but this system has a problem. And one of the problems is that when you try to predict just maybe the next state, a few time steps ahead, you focus quite a lot on learning the low frequency components in the data. And you kind of ignore the high frequency ones because it's harder to predict those. And what happens is that when you run the simulations using your machine learning method, the high frequency components that you missed in your model actually matter a lot when you do long rollouts ahead in the future. And then the solution that some researchers came up with is to incrementally train a model such that you will first focus on capturing these low frequency components, but then you freeze part of your model. You assume that that's fixed, and then you try to focus on learning higher and higher frequency components, and you iteratively grow your model. So it's like a stepwise process of training your model. And first you focus on low frequency components. Once that's fixed, you focus on modeling higher frequency components and so on. And that seems to work quite well. But obviously, this is quite specific of this problem. Yeah, I can imagine in other settings, you may want to have other solutions. So I don't know, I hope maybe that helps.
What does Google think of this question of anomaly detection? I think it's extreme. I will comment in a minute, but please, you have another comment.
I would like to object,
yes.
Not object, the comment to what you said. You said the word frequency, which implies periodicity. The whole thing in this case is that there is no periodicity. So the practical solution which we found in that finance community was to use the opportunity not to predict. We predict conditional probabilities. There are certain situations when we can predict, and because finance, unlike physics, is not supposed to learn everything. You sometimes could pass, not trade, right? So you only have to find predictable patterns and detect whatever is predictable. So conditional probabilities are easier to predict. And then with these conditional probabilities, conditional by big boulder dropped into the pond in my analogy, then it is repeatable and learnable. So that's what I was trying to say. But maybe there is a technique for that which would be kind of more scientific than just not predict what you don't know. So that's
I think Google has handout.
Well, Thomas in this case. So now, with respect to such a situation where something unpredictable might come your way, my colleagues at DeepMind have studied some toy model systems where this phenomenon arises. In particular, they've demonstrated how you can make machine learning models play StarCraft reasonably well. Now, I myself don't know that game that much, but from what I'm observing, apparently as a human player, you would want to have an element of unpredictability in your game that poses extra problems to your adversary, and the methods they developed to handle such types of problems apparently were very effective in handling this. I wanted to make another comment on the previous topic of brittleness, and there I think very important aspect that we perhaps should pay more attention to is that we need to make sure that people in society get a better mental model of how different actually the sort of data processing that machine learning models do is from the sort of data processing that, well, a human typically would do. So machine learning, I personally like to think of it in many use cases more like a kind of alien intelligence than an artificial intelligence. It has some very different qualities to it than how a human would approach problems. And given how pervasive this is becoming, and it really permeates every aspect of life, I think it's important that there's a broader understanding in society that, yes, there are major differences in how machines see an image and how humans would see an image, for example.
Your question strikes a deep chord in me, because a lot of the things that I work on, and I think also many people in this room work on, is AI-assisted fundamental discovery, be it in mathematics or theoretical physics. And one of the fundamental ones is raising conjectures using AI. I'm deeply thinking about, and there we have a problem with anomaly. So just to go back to something that's very close to my heart these days because of Tom and Kyohan, which is number theory. If you take this very simple problem, if you take the number of primes less than a given real number x, less than or equal to a real given number x, just consider that function. You know, it is very well approximated by the integral dt over log t from 1 to x. Just consider that it's you know, it's almost indistinguishably from a distance. Now, if you look at the first million, 100 million, 200 million points, you all see that the prime counting function is always above. I think it's always above or below. Above, I think, right? The integral. So your basic question for me in this context would be, is it even conceivable for an AI assistant system to detect or to predict at some point this is just not going to be true anymore, even though it holds up to 10 to the 10 to the whatever. In fact, skews prove that the first counterexample happens at 10 to the 10 to the 30, around about that. So how could an AI assisted discovery system find such anomalies? For me, this is like the stock market. This problem is a very precise model of the stock market because it has the fluctuations, just like the fluctuations in primes. It's like the fluctuations that's so deep in our uncontrollable region. Bad analogy, I know, but I'm just throwing out this question for any of the panelists to. It's probably a loaded question.
A couple of things. First of all, if I have an AI that can model the stock market, I'm not sat here. I'm gone.
You're not.
I'm not sat here. I'm gone.
You're gone.
I'm
Yeah,
on a
yeah.
beach. I'm not.
But you'll still be here for friendship.
But I mean, so let's. I mean, you know, now the bit that I do see as being different on a more serious point is the reason why mathematicians could succeed in identifying that approximation. Well, it's not breaks down, but the property of it breaks down into the future is because of the deep structures underlying mathematics and numbers and the theory of numbers. It's not from the data up to that point. And I think this is back to the point made before about the problem of training and then looking at out of distribution events. You can't know more than the data you've been given. And this is also back to this point of if you train and what you're learning are the ripples, but you never train on when somebody throws the rocks in, you can't expect it to do more. And I think there's been a sort of slightly societal or psychological effect recently where people will say the words AI or ML and expect miracles. And we should not join that community. Right? I mean, miracles are not something I expect to be able to produce. What you want to do is extract from what's there.
Mhm.
Now, whether a computer with more information than the data of primes through understanding, and we've had talks by, for example, Kevin Buzzard about the mathematical structures could then assist through something like a combination of an RL and a large language model, that I can imagine.
Mhm.
But from just the data up to that point,
Mhm.
no way.
Mhm.
Yeah, I agree totally on this. I think if you wanted to solve this problem, you will need to introduce extra information into your system. For example, your system should be able to know rules of mathematics. I mean, it should be able to use these to understand better the data and maybe use these rules to extrapolate beyond where the data is. But I mean, that problem seems extremely challenging.
Mhm.
I just wanted to say, I was just 2 weeks ago, I was at the Solvay conference for physics, and I was on a panel like this, but it was for the general public. And one of the questions was, can physics be helpful with machine learning to predict the stock market? And if so, why aren't all physicists richer? So just wanted to say that.
Yeah, absolutely, absolutely, yeah.
I can maybe mention another problem that is related and actually quite relevant in practice. One of the areas where I work is on machine learning for molecules. And we are quite interested in predicting the properties of molecules. For example, maybe you have a new molecule and you want to predict if this molecule is going to go inside of a bacteria or not. When you look at the data, one of the things that happens with these molecular data sets is that the data is highly non-smooth. You have something called the activity cliffs, which is, it means that if you change by a small amount your molecule, maybe the property of the molecule changes by a huge amount. And this is extremely challenging for machine learning methods because most methods, they use smoothness properties in your data to try to make predictions. But this data precisely doesn't have these properties. And you know that there are these kind of outliers, although they are not really outliers because the target is correct, but your model is just not able to make accurate predictions in this case. This is one of the most active areas in molecular property prediction at the moment, and it's extremely challenging because you have very few data points and you have this kind of activity cliffs that are very hard to model.
So yes, there's a question there.
We have laws in physics. Would anyone like to suggest whether there are any laws in Probably.
Great question.
And this is a very interesting thing. Machine learning is a very practical field, and you see it from the evolution of deep learning. Deep learning basically evolved from trying things until they work, and they actually work in practice well, but you don't fully understand why. There is a very active area of research in machine learning, which is about the theory of machine learning. And they try to explain, for example, how well a particular method is going to perform in practice, trying to say, oh, you trained your method in this data, you obtained this error. And now, can you say anything about how this method is going to perform on test data? So a lot of people are trying to get theory explaining this, why maybe some networks that are bigger, maybe they overfit more and they generalize worse, and maybe smaller networks, they perform better. There is quite a lot of active work in this area. The main problem in machine learning is that all this work is slightly behind practice. And there is like a big gap between the theory and the practice. You could say, oh, you have these theoretical results. You could maybe use them to construct better methods in practice. And actually what happens is if you try to follow these theoretical results, they don't really are useful at all for making better prediction. It's always better to just try things, see how they work in practice. And if they work well, you keep those. And you don't really use much the theory. Hopefully, as work advances, maybe the theory catches up with practice and maybe the theoretical results become more useful. But at the moment, there is like quite a lot of gap between those.
I mean, I think one of the reasons why things like spin glass theory are useful for understanding machine learning, even though there's a big gap, is because, you know, in machine learning, you're trying to minimize something. And in physics, we're often trying to minimize something. There are physical inequalities, and you know, things are trying to reach the bottom. So so that's a sense in which, you know, the physical laws that we're used to can actually be helpful for understanding machine learning. But I think, so as I was saying, one of the things we're doing is we're using physical systems to do machine learning, where basically the physics automatically does that for you. You know, if you can harness physics to actually, you know, given inputs, calculate outputs, to do the forward computation for you just by minimizing, that's very powerful. And there are a lot of people doing neuromorphic hardware where the idea is to take advantage of that to do basically forward calculations of already trained networks very efficiently with very low energy, and very quickly. But if you actually try to use physics also to do the learning, which is what we're doing, see that you learn by local rules, and you have this coupling of the physical and learning landscapes that I was talking about earlier, it's very interesting because physical laws are what cause these two things to be coupled, and they actually simplify the problem in an interesting way. So I think they can actually make, when you do machine learning with physical systems, I think it can be more explainable because they're physical systems, and there are other advantages as well. So yeah.
So I would say, well, I completely agree with what's been said, that there are laws that people have come up with that are in some sense statistical. And I'm thinking of scaling properties and various other things that people have done. And I could list them. And I've done a little bit of work about how scaling of amounts of data relate to performances and so on. And you can do things like that. But indeed, there is this thing of how useful it is. So as I was working away in Queen Mary and coming up with all sorts of models of AI, absolutely no one was interested in this in a company that wanted to produce an accurate model as possible. That's a slight exaggeration, but in the end, it really feels like, and perhaps this is why it's actually exciting, at the beginning of the Industrial Revolution, when people were making steam engines, there was not the theory of thermodynamics. And the theory of thermodynamics was inspired by the development of steam engines and the Industrial Revolution. And now we are basically building steam engines based on that intuition of putting parts together and making them work. And, you know, it's ironic that at the time when the high-speed 2 rail line has been shut down, at the height of the Industrial Revolution, a train could go from London to Liverpool in 2 hours, which is better than the current state. So it's unclear that we improved anything by understanding thermodynamics. But of course, in the end, it will happen. And it will lead to, once we understand the theory of AI better, we will get developments that we wouldn't have thought of just from playing around. But we're not at that stage yet, I believe.
Just to follow up on.
One of the reasons I asked the question is to regulate something. When you're regulating something, you potentially That was the reason I asked the question.
There's a question from Sven.
Yeah, it's a comment. So I agree with what has been said before. I think one thing to remember is that neural networks are just a dynamical system in the end of the day, whenever we do machine learning. And in that sense, we might not understand the governing rules, etc., writing down the laws right now, what's the best mathematical framework to describe them. But I think we will get there. And in that sense, that also addresses then that question that will provide such a framework as to regulate things, to design things better. It's a dynamical system.
There's a comment or question here. Yeah. Yeah.
So just a brief comment and maybe a question. So I would argue that modern machine learning is not science, but much more engineering, right? A modern machine learning system is very heterogeneous. It has lots of different components. It has lots of acts. It's built by trial and error for a long time until you get into something that works. So the analogy with the steam engine is nice, but it's I think a better analogy is a modern automobile. So what would be the theory of modern automobiles? Of course, underneath it, there's thermodynamics and there's electricity and there's lots of things, right? It's something that's built by putting together many different parts. It's a very heterogeneous system. It's very engineered. It's much more engineering than science. And so I think it's a bit of a vacuous question to ask for a theory of machine learning. It's like asking for a theory of automobiles or the theory of airplanes. There's too many, there are already the theories behind it, but I'm being a bit provocative. I'm exaggerating a bit, but on purpose.
I mean, I'll just quickly do this one. Of course, you're right. But what science often does is give us fundamental bounds. So, for example, the America's yacht race, it's ridiculous. They can now go at insane speeds, many times faster than the prevailing wind. They come out of the water, but in the end, we have fundamental theoretical knowledge of the absolute limit of the system. And we also understand various scaling properties. And the same is true of modern automobiles and what Formula One cars do. That sort of view is what I imagine science provides, even within the engineering realm of ML.
I mean, I think there are aspects of AI that are very similar to engineering. So for example, all these benchmarks, improving the models so that you can get, 2% or 0.002% better prediction, that's really an engineering sort of question. But, all right, I'm going to be unapologetically and arrogantly a physicist and just say, there are times when technology just hits a wall, okay, and it can't go much further by brute force, and you have to come up with something new. And I think that's going to happen to AI. Models can only get so much bigger. ChatGPT-4 already has 10 to the 14th parameters. How much bigger can you get, given that the time that it takes to train it and the energy that it takes not only to train it but to run it? Okay, we're getting really close to that wall. So there's a limit to how much better AI can get. It's just not sustainable. So that's where I think then you really need new ideas. Okay. And that's where physics can do something, that if we understand something about how machine learning works, then we can come up with sort of new ways to think about it and new things to do. And I think that's very interesting physics to think about. But we can't do that without understanding, machine learning. So, so one of the things, the brain uses in a day, it uses about 200 times as much as one ChatGPT-4 query. Okay, but just think about the number of things the brain is doing all day, right? It's a lot more than 200 Chat GPT-4 queries. The variety of things it's doing, the complexity of some of the things that it's doing, it's really amazing. So it's very, very low power. And so I think there's a lot to be gained. So one thing, the brain learns in an analog fashion, it's not digital. That's part of it. It's noisy learning, and it learns by local rules, like neurons that fire together, wire together. So each neuron doesn't have to know the state of every other neuron in order to figure out how to adjust itself to go down the gradient of a learning cost function. That's not how it does it. Okay, so this is where, the kind of stuff that we're thinking about to develop local rules to learn like Hebbian learning, who knows what it will lead to, but it is a different approach. And that's one way that physics can help us, in AI.
Maybe I can say something about the hitting the wall. People started working on these big language models because they just tried them, and then they saw how well they performed, and they just made the model a bit bigger, and they saw it works better, and we make it a bit bigger, oh, it works better. And you can think about extrapolating and see how well it will do. And that's why researchers were spending so much effort. I mean, not researchers, like engineers, for example, at OpenAI. No, they spent a lot of money just training these models because they expected them to work quite much better. And the question is, how is this going to be sustained? And I'm not sure about this, but there are rumors that the OpenAI just trained a massive model, much bigger than anything what they tried before, and they were disappointed because the performance not was what they were expecting. So obviously these rules that you seem to be observing in practice, maybe they get to a point where they don't hold anymore. All this is very speculative because they are only like rumors, not really confirmed.
I think Thomas has a comment.
Yes, so actually there's another limit beyond the effort required for training and then the effort required to run inference with these large models. So another limit here is that we can train on effectively all the data that's available on the internet openly, and at Google, of course, we do this regularly, but we cannot easily scale this up to 1,000 times all the information that has been organically generated by humans on the internet, because that's just not there. So at some point, we also cannot scale up our training set, and that's a further limitation that we are running into. And yes, so the big challenge there is, if we really want to improve performance, we have to find ways to get more out of the data and basically, explore how we can get more of a kind of understanding or machine approximation to some sort of understanding into these models. And that's where the real challenge then lies.
Just to follow up on that, I mean, we like the number 3. Physics begins with the 3 laws of motion of Newton, and thermodynamics begins with the law of the 3 laws. If we're to summarize the 3 laws, I'm just out of ignorance, I don't think I've seen this. What would you say the 3 laws of machine learning are, if you were to formulate it today for posterity? Not to put you on the spot.
Maybe I can say about one very important law. I mean, it's not a. I mean, it's not really a law because you cannot really quantify it exactly on different systems. But a very important concept in machine learning is the bias variance trade-off. And the idea is that when you want to learn from data, you will need to have some bias. And this bias is going to allow you to make predictions. If you don't have a bias, that means that you are considering all possible ways in which the data was generated. When you make predictions, your predictions will be completely irrelevant because you are considering every single possibility. And that means that for a new test point, then everything could happen. So you have to have like at least some bias in your model that will restrict the assumptions, or it will restrict the processes that could have generated the data. The higher this bias, obviously, the larger your error is going to be. And then the smaller the bias, potentially the error could be reduced. But there is another concept which is called variance. And this means that the concept of variance, it means that when you learn from data, the particular data set that you observe is going to change your predictions. And this means that if you repeat the training process over random realizations of the data, you will have high variance in your predictions. And then there is this trade-off where you want a model to have a particular complexity that has the right amount of bias that allows you to learn from the data and the right amount of variance such that the error will be optimal. You can look at this with simple toy problems, but with neural networks also you won't be able to do much because you won't be able to really calculate this bias or this variance before actually training your model and testing it in practice. I think that's an important concept.
So law number one, the bias variance trade-off. Yeah, please.
So a couple of years ago, this is kind of a view that was kind of destroyed by people like Michael Belkin and Ben Recht, and they published a paper, I think 6, 7 years ago, where the paper provocatively called, to understand deep learning, we need to rethink generalization. And they show that whichever way you count complexity of neural networks, they are too complex and they should not work, right? So there's this you've probably seen this double descent phenomenon, which is beyond the bias variance trade-off. So the bias variance trade-off, I'd say it is a perfectly reasonable and very powerful law, but outside of the realm of deep learning, if you are in under-parameterized models. As long as you are in the interpolation regime where you can fit the data perfectly, then that's no longer a law. Let me against and push against also the laws of machine learning. Why not just call them laws of learning? Why would machine learning be different from any kind of learning by any physical agent that is bound by the laws of physics, right? And
yeah. So we got one. We've got 2 more to go.
I've got one then.
Oh, there.
Bayes' theorem.
Okay, that's good.
But seriously, because the point is going back to the things about the bounds and the absolute thing that you can extrapolate. You know, Bayes still tells you a lot, and Bayesian intuition tells you a lot, even if you can't do the integrals. The importance, for example, of a prior, the importance of constructing a posterior distribution based on what you've got. So yes, I'm going to give you a law, Bayes' law. And the one piece of information I'll say about Bayes' law, which I love, for those of you who are physicists and are on the Inspires database, the Bayes' theorem is the second entry on the Inspires database after Principia from Newton. And
in terms of citation,
in terms of chronological order.
Oh right, okay. Right.
So yes, so
nice.
Yes, it's the second.
Nice.
Immediately after Newton. And I like that because, you know, Bayesian intuition is important even if you don't know that you use it, I'm going to claim.
Right. So 1 more to go. We start Bayes, 1, bias variance, and third law.
Yeah. No, I just wanted to say that, I agree with the Bayes rule. Like you can show that if you want to make predictions about unknown quantities, the right way to make these predictions is using probability theory and Bayes rules. And if you don't do that, you will be at a disadvantage. It's great. The problem with Bayes rule is that in practice, you cannot apply it with these big models. So then you move into a regime where this theory is not working fully, and then you need other settings. But you need approximations. You will be doing approximations.
There's still 1 more to go. Anyone?
Sort of observing the different things that have been talked about. I guess, you know, you talked about physical limitations in terms of training times and the scale of how many neurons you have or something. So there are physical limitations. And I've also heard about functional limitations. You know, you can't AI the stock market. So I guess a theoretical question could be, how do we relate the two? And perhaps something has been said already. So if there are any comments, I'd be interested to hear. How to relate physical and functional limitations of AI.
Is that the third one? Oh, you're going to put the three. Okay, so we'll park that question in for a second.
So law number 3 is there's no learning without inductive bias. So you cannot learn anything without bringing something into the table, to the learning process. There's no learning from zero, from zero knowledge.
So that's
I think
the
the
inertia
most
law.
important law.
That's the inertia. We're drawing analogies here. The inertia law is that. Are you happy with this? I don't know.
I'm just going to make one comment. In thermodynamics, it's like they use Python because they start at 0.
Oh, right. Okay.
You've got the 0th law.
So maybe that's the 0th law.
But, you know, just.
Okay, fine. So we still need one more.
Got a laugh over there for Python jokes. That's really good.
Oh, thank you. There's a comment from Thomas.
Yeah, so actually, speaking as a physicist now, I have an issue with this idea that we would want to formulate 3 laws, because whenever we have done it in physics, we basically did it wrong. And let me just make a nasty comment about Newton's 3 laws. So in particular, the third one, actio equals reactio, has created a lot of confusion. And in my personal view, this all gets much clearer if you instead say you must not focus on force as a concept, but the important concept you have to focus on is momentum. And momentum is a charge. It's a conserved quantity, but it's a funny charge. Actually, it's 3 charges, because you can have momentum in 3 different directions in our 3 + 1 dimensional world. And if you charge something up with, well, a momentum charger would be, for example, a gun or a cannon, then it starts to run away. And then it's clear that if momentum is flowing, and it can only flow because it's conserved from one object to another, that gives you that the force that one exerts on the other has an equal and opposite counterforce, because this is just the momentum flowing over. And likewise in thermodynamics, the second law of thermodynamics, what it amounts to, if you actually draw the connection to statistical mechanics, is just the claim that most likely you will find a system in the most likely microstate. So basically, whenever we formulate such laws, we might actually, pedagogically speaking, be making a major mistake.
Yes, please.
I can maybe mention another. I mean, I wouldn't say like rule or or law, but an important concept. It's not so much in machine learning, but more on the decision making setting. And this is the concept of exploration trade-off. And this is quite important in problems where you have to make a series of decisions, or you need to take some actions trying to maximize some rewards. And the way to illustrate this is, for example, with function optimization. Imagine that you want to optimize a function, and you don't really have an access to the function. You can only collect data by evaluating the function at some points. And this means that you will be learning about the function as you collect data. And the question is where you should evaluate your function next, such that you find the minimum of the function fast. And you can show that in this problem, the optimal performance is obtained by exploiting, which means that you try to evaluate the function where your predictions for the function take low values, because you want to minimize the function. You want to collect data where you predict that the function will take low values. But if you want to do optimally, that's not enough. You will need to also collect data where you don't have data so far. And this will be exploration. And this will allow you to discover solutions which you didn't find before. And you can show that if you want to perform optimally in this setting, you need to attain this balance between exploiting a little bit and also exploring. And the optimal balance between these things will give you optimal performance.
Great. I think we got it, right? 0 is the existence of data. 1 is basis theorem. 2, the bias variance trade-off. And 3 is the exploitation trade-off. Done. It's been formulated, and take this down for posterity.
What about the no learning without negative bias? At 0?
That's zero. Yes, we want zero. Yeah. Sorry, there's another comment.
Yes. So maybe what do you think about Occam's razor, where we would look for models that are simplest models that are consistent with data? Do you think that this would be like a good principle in machine learning?
So that's actually taken care of in Bayesians. So you can even prove Occam's razor with BIC. So Bayesian selection will do Occam's for you in model selection.
It's in there.
Awesome. So it's all sorted. Would that address Sanjay's earlier question about functionality? Do these laws now together address your question? Oh, brilliant. Sorry, there's a comment here.
So now we've got to consider why these three laws are actually sending us in the wrong direction, to take Thomas's point.
So 3 + 1. Right. So there's a Kochi has a question.
So this is a kind of provocative question, but so I have so in science, we are wondering why there are laws. The reason why there are laws. So can AI answer this kind of question? Since laws are how we perceive our world, right? And in machine learning, we explore by trial and error how to perceive the world. So, for example, in image recognitions, we look for some good architecture, how to recognize the patterns and such. And in the human history, I think that after trial and error, we found those fundamental laws, right? But we are wondering why there are laws. And in particular, in physics, for example, there are laws for laws, like so action principle. So if you start with action principles, then you can drive equations of motion, right? So those are laws for laws. But we don't know the answer for the question why there are laws. Do you think AI can help us understanding this kind of situation? It may be related to this morning's Thomas lecture on why mathematics is so fundamental and important for describing laws.
Yeah. Okay.
So can I comment?
Yeah.
So
we have a comment first and then Dave.
I think there's an empirical thing that is interesting in this regard. And this is something about just, again, predicting next time steps, etc. If you're thinking about taking just a baseline neural network and trying to do this, and compare this with something where you impose mathematical structure, where you impose something like Hamiltonian dynamics. So you can measure efficiency between those. And so there seems to be a hint, I think, at least in these kind of observations, that somehow using mathematics or mathematical formalisms is actually useful in terms of better capturing the data. So and I find this a very interesting observation, and this obviously can be explored.
I think for this question about we're in danger of moving into philosophy about why there are physical laws. I would say the following thing. We're used to the idea in ML that we have a universal approximation to a function, but that function can be absolutely anything, no matter how crazy. If nature was such that it was completely crazy that there were no good approximations at low energies, which is what we're talking about when we say Newton's laws. It's an approximation at low energies, as you well know, then life would not exist. So I'm going to give you an anthropic argument whereby if the laws of nature were not simple enough for me to write down at my energy scale, a la Newton, then it would be very unlikely that life could be there, because it would be too chaotic to produce the sort of thing required in a metabolic system. That may be unsatisfactory, as most anthropic arguments are. And yet we keep on making anthropic arguments because there will be questions about physics that we don't know, but we can still tie it to the nature of whether, if the thing exists or not, life is possible for us to even make those statements. But I don't see an AI or ML argument as to why there should be simple approximations at low energies or certain frequencies, in particular ML systems, which is back to your thing about partial differential equations with different separations of scales and frequencies. Some will do well, some won't. Arbitrary functions will have frequency mixing and all the other stuff that's nasty.
I think Andrea wanted to say a resounding no.
I'd like to just bring up something that hasn't been talked about yet, but that I think is very important, right? Well, a lot of people think it's very important, and that's explainability in AI. You know, we talked about how we are, due to that double descent sort of thing, we're you know, tend to run artificial neural networks, train them in the over-parameterized regime, which means that there are many solutions. And as a statistical physicist, I find that very interesting because each solution is a member of an ensemble that of states that do exactly the same thing. That's exactly the ensemble that you want in order to understand sort of how the microscopic things of tuning node weights are leading to this collective phenomenon of learning this thing. And we know from statistical physics that what you need to do is some statistical analysis of this ensemble. I haven't heard very much about that. I haven't heard about people doing that. And so, you know, as I think you can all tell, I am not an expert in machine learning. So I would like to ask the others on the panel who are, do people do that?
Sorry, what is the question?
Do people use all the solutions that come out of the same problem due to overparameterization? There are many, many solutions. And do they study that ensemble of solutions statistically to try to extract out how the node weights, basically to get at explainability? Okay.
I think some people, they work with this approach of considering all possible ways in which the data could be explained. And there are some methods that they do this. One example is Bayesian methods. They will consider actually all possible hypotheses, and they will weight each one by their probability. You have also ensemble methods where they will be considering multiple ways on modeling the data. And at the end, you just average the predictions of all these methods. You usually get gains in performance. But for explainability, I think it's, I mean, you could try to explain these ensembles and maybe you will get more insights on what's going on. I think machine learning methods are very good at finding patterns and regularities in the data, like this kind of laws that could be present in the data. And they might be able to explain why something happens in the data, maybe because these variables take these values or so, then you get this output. But I think it's very hard for these methods to actually tell you why there are some laws in the data. I think that's beyond whatever they could be doing. They just discover things present in the data. They might be able to explain why for some particular settings of the input variables, you get a particular output, and you may be able to get insights about the properties of the data using these methods, but explaining why there are these properties present in the data, it goes beyond what the methods can do.
That wasn't actually what I was asking, because, you know, in statistical physics, right, the whole point is to get microscopic insight into collective phenomena, like, oh, you know, in the Ising model, the fact that it's binary is what gives you this set of exponents, right? You know, for the critical point. What is the key feature of that those microscopic properties that give you the collective phenomenon? And that's the whole question of explainability in AI. The neural network gives you a certain answer, Okay, what did you do in that neural network, microscopically tuning node weights that allow that answer to emerge, right? What is it? And we know from statistical physics, you can't just look at one example and learn anything. There's too much disorder. You have to look at a whole ensemble of answers if you want to get that answer. And that's what I haven't seen people do to try to understand, okay, how tuning node weights leads to emergent learning.
I think we've got to be, we're in danger of discussing semantics, but explainability in AI doesn't always mean what you said. So to a lot of people, it's more like the AI comes up with a prediction and it wants to say why. It's chosen a cat versus a dog. God knows why they love cats and dogs, these AI people. And then they want to go, what features in the photograph lead it to choose it to be a cat or whatever. So that a lot of people like that as an explainable thing. Now, the thing about doing ensemble studies of neural networks is definitely people do. And in fact, we've done some, and we do that in our work because we're applying notion of quantum field theory, which requires doing ensemble techniques. I think, but I know what you mean. You're looking for, you're ordering, yes, no, a specific ensemble, exactly. I completely understand, yeah. And then you want to establish order parameters and things like that, I'm guessing, yeah. Well, I think people look at it, but it's not been very successful as a program, mainly just because of computational cost. Because you've got to run these things again and again and again. And if you're doing a hard problem, then, there's compute costs, which are quite prohibitive. For simple models, you can do it, right? You can run MNIST and learn something.
Thomas has a comment.
Yes, so first of all, with respect to this question, would people study ensembles of neural networks? It, pragmatically speaking, depends a lot on the application. So for example, if we are training a large YouTube recommender system model, then what one would generally observe is that this works remarkably well. If you have experience with training smaller models, then you kind of would know what to expect, and you would get some variability if you rerun training a few times. But these very large models, they often train amazingly well. You set up training, and then it's about like many roads lead to Rome, and you always get something that's pretty much equivalent to perhaps even the global optimum, if such a thing exists. And that's kind of surprising here, but typically then you are happy because this is then the thing that you're deploying in production, and then you don't ask further questions about this. Now, with respect to the earlier comment about can machine learning be used to actually discover new laws? Now, if we are talking about such a thing, then the fundamental thought that's underlying such laws very often is using physics terminology, some conserved quantity, or using computer science or mathematics terminology, some invariant. And just from personal experiments with, in particular, large language models, talking to transformers, I get the impression that what we currently have is overall not that great at actually performing correct reasoning with invariants, but I cannot say much more about this because it might or might not be related to something that I might be brewing at the moment. So there might be some activity going on in that particular space. Now, in terms of how we as humans went about developing physics, it should perhaps be pointed out that astronomy played a very important role early on. And we also have to see the roots in astrology here, which no one is talking about anymore, of course. But people really struggled to make sense of the world, and they thought that the stars might have some influence. And then they studied the stars closer, and they found that this is actually a nice system where, as we understand it now, the interactions between the different bits and pieces are mostly decoupled. So we can mostly study the orbits of planets by talking about two-body systems. And that, of course, helps a lot now if we were a civilization of aquatic creatures on a planet that's well, where the sky is always cloudy and you never would see the stars, then perhaps we wouldn't have developed something like the physics that we have here and today. So the question is, to what extent was it a fortunate accident that the world we experience and we inhabit is just such that we could develop that approach and actually could push it quite far.
I think we are, in the interest of time, I've been given the important duty of shepherding everyone to coffee. But let's first thank the panelists for their wonderful contributions. And let's have 5 minutes for questions from anyone who might have anything of interest.
At some point you mentioned that AI cannot do miracles. And there were a few examples, like the one of Jan with the prime numbers or the stock market. In your respective fields, do you see particular problems that are not amenable to machine learning besides the ones that we saw already? Yeah, I mean, which other problems you see that might not be, well, or have fundamental obstacle to be approached with machine learning or artificial intelligence, or the artificial intelligence techniques and technology that we have at the moment?
Maybe what I can say is more focusing on the limitations of existing machine learning methods. We have mentioned this thing of extrapolation. No, these methods, they fail catastrophically when you try to extrapolate. And I think that sometimes they are very data hungry. So you will need like tons of data to actually make good predictions. And in many settings, you won't have that much data available. An example is this molecular property prediction problem. So those are like very difficult settings. And another example is that, another example of these limitations of machine learning methods is that many times they will find associations between input variables and outputs, and you may make predictions, but you have to be very careful when you use these methods to try to understand your data. They will, for example, just capture any particular correlations or dependencies present in the data, and some of these could be spurious. Maybe they are originated just because you have biases in the way you sample the data. A typical example of this is when you have pictures of cows and camels, and you have like the cows have green fields in the background and the camels have deserts in the background. And then your classifier may just look at the background pixels and say, oh, there is a green field, this is going to be a cow, or there is like a desert in the background. And when you test these methods then in new settings, where these biases present in your training data don't occur, then they are going to perform poorly. And people are working basically trying to reduce these limitations, making deep learning more data efficient, making it more uncertainty aware, as I mentioned, so that you know maybe when it's going to fail because you are in this out of distribution regime, or trying to capture only try to avoid these spurious correlations present in the data. I know there are probably more. I cannot think more about that now.
Sorry, there's Thomas has a comment.
Yeah, so in general, what we do with machine learning, the way we are applying it these days, is that we are drawing examples from a given probability distribution And then we try to learn something from observing these examples. Now, if there is no such probability distribution that's underlying, and of course there are things that just don't have a probability distribution, then we are totally out of luck with that method. And also, of course, if we have a probability distribution that has its black swans, that does weird things, then naturally that would also give us trouble. And I think I can make this prime number, so the integral ln x over 1 over ln x dx, I can make this even a bit sharper with Borwein integrals. So if you take the integral over the axis of sine x over x, that gives you pi half, because, well, it's just the Fourier transform of the indicator function of the interval from -1 to 1 up to, well, that factor to pi over 2. If you take integral sine x over x times sine 3x over 3x, then that's a product of two such Fourier transforms. So if you go back, it would be a convolution, and well, then evaluate it at 0, because, well, you're picking out the value at 0 with the integral. And well, if you look at it in real space, not in Fourier transform space, then you are evaluating at 0, and convolution of an indicator function of an interval with from -1 to 1, with another one that goes from -1/3 to 1/3. So you still are at 1 at 0. So basically this integral also gives you pi half. And if you multiply in an extra factor sine 5x over 5x, you still get pi half if you work out the integral. This one goes wrong at first if you multiply factors up to sine 15x over 15x. And if you did something else like sine x over x times sine 100x over 100x times sine 300x over 300x, and continued like that, then the first 10 to the power 42 such integrals would give you the value pi half, and then it breaks down. And of course, you would have no chance whatsoever getting any clue about what's going on by observing patterns in the output. You would get totally misled there. And that sort of understanding that you would need to have in order to come to the correct conclusions, that's something that at the moment I don't see yet with the technology that we have.
In the interest of time, if there are no further questions, let's head to coffee. Thank you very much again.